Quiz question 10 of 17, also known as Think and Solve 3.42. A car takes 10 seconds to go from a velocity of 0 to 24 meters per second at a constant acceleration. So then, what is that constant acceleration? What if we needed to use that acceleration value in this equation, for example? So I'm just referencing statement 1, 2, and 3 to reinforce this distance equation, this equation that relates distance, acceleration, and time. That's just background. This question wants you to solve A, which is pretty straightforward. A stands for acceleration. The definition of acceleration is change in velocity over change in time. Change in velocity is final minus initial. So in this case, delta. Delta V is final minus initial. So delta V is final velocity minus initial velocity divided by change in time, which is final time minus initial time. I plug in numbers. My final velocity is given. My initial velocity is 0. That's also given. My final time is 10, and I just use 0 as my initial time. So very straightforward. You can see 24 divided by 10 is 2.4. But as always, I'm going to stress dimensional analysis. The answer is 2.4 meters per second, or saying the same thing another way, 2.4 meters per second squared. And how did I get meters per second squared? Right here. I simplified. I did dimensional analysis. I multiplied by the number 1. This is how I write the number 1. If the numerator is the same as the denominator, that is the number 1. And then I do some cancellations, and that's how I end up with 2.4 meters per second squared. Quiz question 11 of 17, also known as Think and Solve 3.43. A ball is tossed with enough speed straight up so that it is in the air for several seconds. Part A, what is the velocity of the ball when it reaches its highest point? That's pretty easy, I think. Here's a ball down here. This blue ball is down on the ground, and then you throw it up, and it rises up, and at some point it reaches 0 velocity. So it's going up, it reaches 0 velocity, and then it falls down. So for part A, the final velocity at the highest point of an object's trajectory is 0 meters per second. Part B says, what is its velocity 1 second before it reaches its highest point? So here, again, here's the ball when it's first thrown up. You give it some initial velocity. And we want to know 1 second before it reaches the very top, before it hits that 0 velocity point. 1 second before that, down here, what is the ball's velocity? So equation 1 here, number 1, step 1. This is the green sheet equation that relates velocity, gravity, and time. So I'm just starting with this green sheet equation. The final velocity is 0 because of what I said about part A. It slows to a stop at the very top. The initial velocity is what we're looking for, so now we just plug in the numbers. Final velocity is 0. Initial velocity is what we're looking for. G is 9.8, so this is minus G, which means minus 9.8. Remember, G is itself positive 9.8. Just want to reinforce that. And 1 second is time. So you multiply everything together. Well, I should say I'm going to get the initial velocity all by itself, which means I'm going to add 9.8 meters per second squared times 1 second. I'm going to add all of this to both sides, and then that's how I solve for 9.8 meters per second. I'm adding this term, this again, 9.8 meters per second squared times 1 second, adding it to both sides, and that's what's leading me to this final answer. Part C, during this 1 second time interval, what's the change in velocity? Delta V means final velocity minus initial velocity. In fact, delta anything means final minus initial. So in this case, the final velocity is 0 meters per second at the very top of the trajectory minus the initial velocity, which is 9.8 meters per second. That came from this work here. So 0 minus 9.8 meters per second is negative 9.8 meters per second. This negative sign makes sense because I'm slowing down. Negative means I'm losing velocity. Part D, what is its velocity 1 second after it reaches its highest point? So here, right here, the ball is at its highest point. Now we say its initial velocity is 0 meters per second. So notice that flip. It's not final velocity, it's initial velocity that equals 0 meters per second. And 1 second later, it has fallen downward. The final velocity is what we're looking for. Here's that same green sheet equation. My final velocity is, again, what I'm looking for. And initial velocity is 0. Negative g means negative 9.8 meters per second squared. And I get my final velocity 1 second after reaching the top of its trajectory is negative 9.8 meters per second. And again, that negative makes sense because I'm going down. Whereas over here, this is positive. So this positive 9.8 meters per second makes sense because the ball's going upward. Part E, what is the change in velocity during this 1 second interval? So in this case, delta V is final minus initial. My final velocity is negative 9.8 meters per second. That's what we got here. And my initial velocity was 0, starting from 0. So that's how I'm getting negative 9.8 meters per second. So interestingly enough, delta V here is the same as delta V here. My change in velocity going upward for that 1 second interval is the same as the change in velocity when I go downward during that same 1 second interval. Part F, what is the change in velocity during this 2 second interval? So we're talking about this blue ball right here going up during that 1 second interval and then coming down for another 1 second interval, which is that 2 seconds. And in this case, delta V is final minus initial. Final velocity is this negative 9.8, and that comes from here. This is the velocity I'm using that corresponds to what's happening at the end of that 2 second interval minus the initial velocity. The initial velocity is right here. This is the initial velocity at the beginning of that 2 second interval. 9.8 is right here. This was my velocity at the beginning of the 2 seconds. And right here, negative 9.8 meters per second was the velocity at the end of that 2 seconds. And part G, what is the acceleration of the ball during any of these time intervals? So this is always the same. If an object is going up, or if an object is going down, or if an object is momentarily stationary, no matter what's going on with free fall, the acceleration is always in this negative 9.8 meters per second squared negative direction. Could be going up, could be going down, could be stationary. No matter what it's doing, it's always accelerating downward. Quiz question 12 of 17, which is Think and Solve 3.44. You toss a ball straight up with an initial speed of 12 meters per second. Part A, how high does it go? I'm thinking of using this green sheet equation because there's distance. There's my final distance, and that's what I'm after here. The only problem is I don't know time, so I'm stuck, which often happens. And so what I'm going to do is go back and look at the green sheets, and hopefully by now I'm practiced enough so that this would be a natural alternative that I would consider, which it isn't until you do some practice. I'm going to try this green sheet equation. I don't see distance anywhere here, but I do see t for time. So maybe I can find time from this equation and then go back to this equation and use time to get my final answer. So step 4, as mentioned, this projectile, when it reaches the top of its travel, the peak of its trajectory, comes to a momentary stop. So V final is 0. So if I am using this equation, V final is 0 equals V initial minus GT. And here's how I'm going to get T all by itself. I'm going to add GT to both sides, which means on the left side, I have GT. On the right side, I only have V initial because this GT and that GT eliminated each other. And now what I'm going to do is I'm going to divide both sides by g. Divide the left side by t, which means I have to divide the right side. I should say divide the left side by g and divide the right side by g because I do want to get time all by itself. So if I divide both sides by g, these two g's cancel out. I'm left with t. My right side becomes v initial over g, and then I just plug in the numbers. So you can see here, and I'm showing that 12 divided by 9.8, according to my calculator, is about 1.224 seconds. But here, what I'm doing here looks kind of complicated, but I am multiplying by the number 1. I have a fraction here. This numerator is the same as this denominator. They're both seconds squared over meter. So anytime you have the numerator and the denominator equaling each other, basically being the same thing, that is the number 1, and you're allowed to multiply anything by the number 1. And if you cancel what is cancelable, I am left with seconds. So this is what I'm hoping to see. I'm hoping to see my answer left in seconds, my answer expressed in seconds, which it is. So I got t, number 10. Now I'm going to go back to this equation from the green sheets. But this is tricky again. So this is a pretty tricky problem. Careful, this equation applies to an object that is falling. In this case, the object is rising. So let's flip it. I'm just going to turn everything upside down. I'm going to call this initial distance. This is my final distance. And number 12 here, here I am processing my equation. So df is 0, it's at ground level, equals d initial, which is what I'm after, minus 1/2 gt squared. Again, just using this formula. And now I know what t is. Step 13, what should I do? I'm going to add 1/2 gt squared to both sides, as you can see here. Whatever I do to the left side, I have to do to the right side. And I'm adding this to the left side because I want to get initial distance all by itself. So I'm left with step 13, 1/2 gt squared equals di, the initial distance. And this initial distance is the distance I'm after. It's saying, hey, how high does the ball go? So this is how I'm approaching it. Little creative thinking here. Step 14, I'm plugging in numbers 1/2 times g times time squared. If I plug the numbers into my calculator, I get 7.34 meters, which is the correct number. Don't forget this is squared, so I'm not multiplying by 1.224. I'm multiplying by 1.224 squared. So it's 1/2 times 9.8 times 1.224 squared. There's my dimensional analysis, which I can't forget about because it's a great red flag indicator. And I get the right answer. Part B, how long is it in the air, neglecting air resistance? And I'm noting that the ball, this projectile, takes a certain amount of time to travel up and then the same amount of time to fall down. So that's why I'm saying the total time that it's in the air is the time it takes to go up plus the time that it takes to go down. And those are the same time because what goes up must come down. So I'm just multiplying this t value that I got way back here by 2. This is a difficult problem, but the thinking is you've seen it. If you can take some time to maybe digest it, going forward, a problem like this may not be that bad. Problem 13 of 17, which is 3.45. Surprisingly, very few athletes can jump more than 0.6 meters straight up. I need to figure out the hang time for this athlete. The hang time is the amount of time it takes to travel upward plus the amount of time it takes to travel downward. I'm going to stay true to my green sheets. This is my green sheet equation, which comes from your textbook, and it's basically describing the distance traveled by a falling object. Now, in this case, I have a rising object. So my object's going to rise and then it's going to fall. So I'm just going to look at the portion of this situation where this athlete is falling back to the ground and then just double the time. So what I have here is my final distance is 0 because that's ground level is 0. And my equation says now 0 equals the initial distance minus 1/2 gt squared. I'm going to add 1/2 gt squared to both sides because my goal is to get t all by itself. So if I do that, I get 1/2 gt squared is on the left side, and d initial, the initial height, is on the right side. And remember, whatever you do to the left side, you have to do to the right side. So now what I'm going to do to equation 3 is multiply by 2. I'm going to multiply the left side by 2 and the right side by 2. So my left side now becomes gt squared, and my right side is 2 times d subscript I. I'm going to divide both sides by g, and now I get t squared equals 2 times d initial divided by g. The last thing I'll do is I'll take the square root, because remember, I got to get t all by itself and then double it. So t, whatever I do to the left side, I do to the right side. My left side is now t. My right side is this expression, 2 times d initial divided by g. And now I'm just plugging in numbers. I'm doing the dimensional analysis. My calculator says t equals 0.345. Dimensional analysis does make me confident. I'm getting the square root of seconds squared, which is seconds. Number 8, I multiply by 2 because, again, what goes up must come down. And my total hang time is 0.7 seconds. And again, this is a little bit tricky until you get used to it. I'm flipping things upside down. So I'm just looking at the fall case. And I know the time it takes to fall is the same as the time it takes to rise. So that's a little creative. Question 14 of 17, which is Think and Solve 3.46. An airplane with an airspeed of 110 kilometers per hour lands on a runway where the speed is 40 kilometers per hour. So this problem is meant to illustrate something known as relative velocity and also the vector nature of velocity. So here's what I have for part A. What is the landing speed of the plane if the wind is head on? This black dot represents the airplane, and this arrow represents the airplane's velocity vector, which is 110 kilometers per hour. It's flying into a headwind of 40 kilometers per hour, which is another velocity vector going in the opposite direction. That's what it means to be a headwind. So if I just add these two vectors together, I have this black vector added together with the red vector, which is going in the opposite direction. And the net result is this green vector that you see here. So from a numbers point of view, 110 minus 40 equals 70. From a visual point of view, again, I have this black vector added with this red vector to give you that green vector. Part B, what if I have a tailwind? I have the same airplane and the same airplane velocity that it's exhibiting upon landing. And now the wind is coming as a tailwind. So I have the red vector added with I have the red vector added with the black vector, so they're additive, and now I have 150 kilometers per hour going to the right. Because remember, a vector is a magnitude and direction. Last but not least, what if I'm coming in for a landing at that same 110 kilometers per hour, but now the headwind is 110 kilometers per hour, which means in the opposite direction. If I take this black vector, which is the airplane's landing velocity, direction is to the right, magnitude is 110, you can see that it's going to be completely canceled out. The black vector plus the red vector equals 0. So my landing speed is technically 0 kilometers per hour. I don't think you need any help from me for this question. It's the same situation. We have a mosquito flying 2 meters per second relative to the air against a 2 meter per second headwind. So just draw the vector that represents the mosquito's velocity, and then draw a second vector that represents the headwind, and you add those two vectors together, and you're going to see the result is 0 meters per second. This is illustrating, again, the vector nature of velocity and how you deal with them. Problem 16 of 17, which is Think and Solve 3.48. What is the speed over the ground of a mosquito flying 1.3 meters per second relative to the air caught in a 1 meter per second right angle crosswind? This black vector represents the mosquito's velocity, 1.3 meters per second going to the right. It didn't say it was going to the right. That's just me saying, hey, I'd like it to go to the right. But I do know that the crosswind is at a right angle to whatever the velocity is by the mosquito. So that's why I'm drawing this red vector to represent the crosswind. It has to be at a right angle because that's what it means to be a crosswind. And it also has a velocity of 1.3 meters per second. So the length of the black vector is the same as the length of the red vector. They have the same magnitude, but their directions are different. So now I'm going to use the Pythagorean theorem. And again, you might be used to seeing something like a squared plus b squared equals c squared. It's the same exact same thing here. So I would say, well, in my case, I'm going to do 1.3 meters per second squared plus 1.3 meters per second squared equals the question mark squared. And again, don't let this throw you. You're used to a squared plus b squared equals c squared. It's the same thing here, just the names change, but the math is the same. So if I square 1.3 and then I add it to 1.3 squared, I get a result. I take the square root of that result and I get the correct answer. Basically, here's the same problem for the last quiz problem. Select the correct equation that shows the speed of a bird that flies 10 kilometers per hour in a crosswind of 10 kilometers per hour is about 14. So I'll just do some general talking, but maybe come back to the Pythagorean theorem again a little bit. The Pythagorean theorem, as you might remember, is when you have a right angle triangle, which means this black vector is at a 90-degree angle with respect to the red vector, you could say a squared plus b squared equals c squared, and that's what I have here, just general Pythagorean theorem. So I have the exact same triangle, but now I'm calling A 10 kilometers per hour and B 10 kilometers per hour. So in this case, the net result, the speed of the bird, would be c, and c is the square root of a squared plus b squared, where a equals 10 kilometers per hour and b equals the 10 kilometer per hour crosswind. And the only equation that is correctly describing that is this first equation in my case.